Hello everyone, I'm Haoran Yu, a final year PhD student at Georgia Tech and a supervision professor in NeurIPS. Today I'm very excited to present our work, ShiftAddLLM, accelerating pre-trained large language models via post-training multiplication-less reparameterization. The background is that powerful large language models are hard to be deployed because of two reasons. First, they have extensive parameters and memory usage. For example, GPT-3 has over 170 billion parameter size and needs 350 gigabyte GPU memory, requiring larger than 5 GPUs to hold the model weights. Second, they have a lot of dense multiplications. For example, GPT-3 performs 10 to the power 15 flops for a single forward pass. Previous solutions for efficient large language models deployment includes post-training quantization, either uniform quantization or weight-only quantization. Uniform quantization quantizes both weights and activation and is practically limited to 8 bits, for example, LLM.int8 and smooth quant. Weights-only quantization is more often used since the weights are the larger bottleneck, for example, OPTQ and AWQ. The advantage of such PTQ is that they can directly quantize the pre-trained large language models without fine-tuning. But the disadvantage is that such PTQ methods still have many multiplications and need dequantization for leveraging existing GEMM kernels. Another solution is to reparameterize multiplications in LLMs with shift and adds, which can lead to up to 31 times unit energy reduction and 26 unit area reduction compared to multiplications. However, previous shift and add reparameterization methods needs either full parameter training or fine-tuning to recover accuracy, which is hard for large language models due to lacking data and compute. So we propose to reparameterize the pre-trained large language model with shift and adds in a post-training manner, seeking mathematically equivalent reparameterization. And there are three challenges. The first, how to effectively reparameterize pre-trained LLMs with shift and add. Second, how to mitigate the accuracy drop of shift and add reparameterization. Third, how to automatically determine the number of bits for each layer. And our contributions address them one by one. Before zooming into our method, I want to first provide the preliminary of binary coding quantization, or BCQ, as our ShiftAddLLM is based on this. BCQ quantizes a given weight vector into a series of binary matrices and scaling factor matrices. For example, if we consider 3-bit quantization, then we have 3 sets of binary matrices and also 3 sets of scaling factor matrices. The binary matrices are of the original shape of weights, while scaling factor matrices are much smaller. If we consider 1-bit quantization, by which I mean the Q is 1, then this optimization problem collapses to binary neural network and has the analytical solution like this. However, for multi-bit quantization, there is no analytical solution. Current state-of-the-art optimization approach adopts greedy methods and alternative methods. For greedy method, the idea is that ith-bit quantization is performed by minimizing the residue of I-1 bit quantization. So once we have an initial bit solution, we can use the remaining bits to gradually minimize the remaining errors. And for alternative method, it's one step further of the greedy one. It leverages greedy methods to initialize alpha and b, and then iteratively updates them for minimizing the quantization error. And our ShiftAddLLM is built on top of such BCQ. And it gets rid of both retraining and dequantization, which also maintain the task accuracy. Specifically, the idea here is trying to further quantize the scaling factor to powers of 2 and leverage lookup tables to accelerate the multiplication with binary matrices. And overall, computation flow is like this. We further multiply the scaling factor matrices with the input activation. It's noted that here the scaling factor are quantized to power of 2, so the multiplication can be replaced by bitwise shifts. After that, we need to multiply the shifted activation with binary matrices. So instead of directly multiplying them, we first construct lookup tables where binary matrices are keys and partial sum of shifted activation is values. Then we can directly query and add to avoid dequantization. I'll zoom into these two steps for elaboration. For the first step, the activation is still in the FP16 format, and the multiplication between a floating point number and a positive or negative power of 2 integer can be efficiently implemented by an integer addition instruction. For example, here, if we multiply 3.14 with minus 2 to the power of 2, then we only need to add the power of 2 integer to the exponent part of the floating point numbers. And for the second step, instead of multiplying the floating point number with binary matrices, we first construct the lookup tables. For example, we pre-compute 256 possible values for every 8 elements in the shifted activation to construct the lookup tables. If the shifted activation is the n-dimensional vector, in this case, we will get n over 8 lookup tables. For lookup tables, the grouped binary weights are used as keys, and every 8 grouped binary weights form an AB key, and the pre-computed partial sums are stored as values. This allows us to handle the multiplication between the binary matrices and the shifted activation as queries to the lookup tables. And we then add all the partial sums to obtain the final output activation still in FP16 format. Such lookup tables are well supported by existing GPU kernels so that we can achieve real speedups on GPUs. However, directly reparameterizing the large language model leads to degraded accuracy. So our second contribution aims to boost the accuracy after adopting multi-objective optimization. Previous work either minimize quantized weight error or output activation error, like the LUT-GMM and OPDQ. But they are actually conflict with each other. For weight objective, previous method adopts scaling factors for each row of the quantized weight. However, this does not optimize output activation error because as each weight element is multiplied by a unique input activation before summing to produce the output. So varying input activation can rescale the weight quantization error differently, causing large divergence in the output activation. For example, LLT-GMM adopts this weight objective. On the other hand, the activation objective works by focusing on reducing the output activation error. It quantizes one column of weight at a time and adjusts the remaining unquantized weight to make up for any error caused by the quantization process. However, since the scaling factor used in this method are fixed, they may not be flexible enough to accommodate the changes made to the weights after each adjustment. A method called OPDQ used this optimization objective. To reduce the accuracy loss after reparameterization, we introduced a multi-objective optimization framework that can combine both weight and activation objectives using scaling factors applied to each column instead of each row. The idea here is that the column-wise scaling factors solve the issue from the earlier weight objective, where varying input activation could rescale the quantization errors. Here instead, each scaling factor is tied to a constant input activation. So when we optimizing the weight objective, the output activation quantization error is also minimized. On the other hand, when we're optimizing the activation errors, scaling factors for the subsequent columns are updated gradually after compensating for the corresponding column's weight. So that can ensure a better fit than the previous activation objective. And the column-wise scaling factor design significantly boosts the accuracy after reparameterization. However, it does not fully leverage the BCQ, which processes 8 elements per row of weights in parallel as lookup table keys. resulting in latency overhead for models with larger than 30 billion parameter size. So to address this, we propose a blockwise scaling factor design that can group 8 columns and 1/8 of the original rows to share a scaling factor. So this way, we can ensure the compatibility with the BCQ kernels and achieve the latency reductions on GPU. And we refer to ShiftAddLLMs with column-wise scaling factors as our accuracy for higher accuracy optimization, and with block-wise scaling factors as our latency for optimizing accuracy-latency trade-off. And the third contribution is how to achieve mixed and automated bit allocation. Our layer-wise sensitivity analysis revealed that different layer or blocks are not equally sensitive to reparameterization. And we propose to automatically assign bits based on a criteria proxy that accurately predicts the reparameterization error with much less time and cost. And here show the overall objective for optimizing the bit allocations. The goal is to minimize the sum of the criteria C of all layers and the budget B per layer. We evaluate ShiftAddLLM across 2 tasks, 5 types of models, and against 4 SOTA baselines. The overall comparison showed that our ShiftAddLLM achieved average perplexity reductions of 5.6 and 22.7 at comparable or even lower latency compared to the most competitive quantized large language models, at 3 or 2 bits respectively. And it can also achieve more than 80% memory and energy reductions over the original large language models. So to summarize, we propose the ShiftAddLLM framework, which aims to accelerate pre-trained LLM via a post-training ShiftAddLLM reparameterization. And our ShiftAddLLM features 3 contributions. First one is the ShiftAdd reparameterization. The second one is how to leverage the multi-objective optimization to recover the accuracy drop. Third is the automated bit allocation strategy that determines the optimal number of bits for each layer. So that's all for the presentation of ShiftAddLLM. If you have any questions, feel free to drop an email.